Welcome class and welcome to another lecture in Sustainable Energy Technology course. So in the previous class, we began our discussion of renewable energy systems in general, and we also looked into some of the differences between renewable energy and conventional energy supplies. So today we will continue our discussion on renewable energy technologies, the main renewable energy sources that exist today, and what is their situation compared to other types of energy sources over the last decades, how they are growing, what are the trends of their growth, etc. And then if time permits, we will discuss a little bit, start our discussion on hydroelectric energy systems or hydropower plants. So when we discuss renewable energy systems, there are certain terminologies that help us understand the efficiency or the effectiveness of a certain renewable energy technology, renewable energy transformation technology. Some of them are common with traditional energy systems as well, while some others are more novel as they are far more important in renewable energy technology than non-renewable or fossil fuel based energy technologies. One parameter that is very common everywhere in all energy conversion systems and devices is the quantity called efficiency eta. So this is the useful energy or the work output that you are getting out of your system by the total energy input into your system. So for example, if you have say a power plant or a solar farm that is converting the primary energy source. For a power plant, say a natural gas power plant, it will be the chemical energy content of natural gas that is being fed to the system. And for a solar power plant, it will be the total energy flux that is being captured by the solar cells in the area of its operation. So that will be the total energy input, which is our denominator. And the useful energy or work output will primarily be the electricity, the electrical energy that is being generated out of that power plant or out of that solar farm. The ratio of these two is the efficiency eta. So this idea of an efficiency where the useful energy or work output divided by the total energy input of a system kind of is useful both for renewable and non-renewable energy sources and technologies. Another important parameter that is perhaps more important in renewable energy sector is the annual capacity factor Z. What is Z? It's the energy generation station delivers over an entire year by the energy that it could deliver at its maximum capacity over that same year. Okay. So the actual energy it delivers in say gigajoules or kilojoules or megajoules, and the energy it could deliver if it ran 24/7 at maximum capacity throughout the year. That is the denominator and this one is the numerator. So this kind of gives us a sense of how much of its maximum capacity is being utilized by a given power plant or an energy generation system. Why is it important? As we will see, renewable energy systems often do not work most of the year at its maximum possible capacity. Hence, its capacity factors are often less than 1. In much later in the class, when we will discuss electric grid systems, we will also see this effect that the maximum capacity of many kinds of plants is much larger than the actual energy that it is delivering. There are things called the peak load power plants, which only come online when there is an excess demand of electricity that the general power plants cannot meet, a sudden spike in demand. So these power plants only remain operational during that period when there is an excess demand and then again stop working. So for such power plants, the capacity factor Z is much smaller than, for example, what is often called a base load power plant, which is running all year through at its rated capacity. So we will discuss these aspects and how the capacity factors of renewable energy systems make it suitable primarily for peak power or intermediate cycling power plants much later in the class, whereas base load power plants are much difficult to replace by renewable energy systems. So for example, here 1 year is around 8,760 hours. So if the maximum capacity or rated capacity is given as in kilowatts, what is the maximum capacity at which your energy transformation system, be it a power plant, be it a solar farm, can run? Suppose it's given in kilowatts, then the denominator is Cmax into 8760 kilowatt hour. That's the energy it can deliver in an year period. Okay. And what is the actual energy it is actually delivering? That's the E actual in kilowatt hour. And these two will give you the capacity factor Z of a power plant. Another important variable is what is called the full load hours. Okay. So here it's the maximum capacity. Here C0 is what is called the rated capacity. The rated capacity is the one which the manufacturer says the system should be running at. Okay, this is usually somewhat lower than the maximum capacity. Sometimes they are the same and they can be used interchangeably in some cases. But we define what is another variable called the full load hours in terms of the rated capacity. And how do we do that? So what is called full load hours, T suffix F, is the actual energy that the power plant delivers over a year in terms of kilowatt hour divided by its rated capacity in kilowatts. Okay, so the rated capacity is a power variable, so its unit is kilowatt, similar to maximum capacity. So the capacity rating is basically the power rating of your system, how many joules of energy it is delivering per second at its rated value or the maximum possible joules of energy it can deliver, which is Cmax, the maximum capacity. So here C0 is in the denominator and at the top is the actual energy it is delivering throughout the year. So in this context then, this unit is kilowatt hour by kilowatt. So the unit here is in hours. So that is why it is called full load hours. So physically what it means is, it is the number of hours this power plant has to run at its rated capacity for it to deliver the energy that it actually delivered over the period of a year. Okay. So suppose 1 year is 8,760 hours and you hear that your full load hour is 5,000. Okay. So the power plant simply had to run for 5,000 hours at its rated capacity to deliver the energy that it actually delivered over that period of year. If this full load hours was 8,760, it means that the power plant ran at its rated capacity throughout the year non-stop 24/7, which does not usually happen. So again, the full load hours is usually less than the total number of hours in a year, which is 8760. So often this capacity factor Z and the full load hours are important parameters for renewable power systems because they do not operate at full or rated capacity for many hours in a year. Okay. So for example, think of a solar plant, solar farm. Clearly, it does not generate any power at night. So over course of a 24-hour day, for 12 hours, it's non-operational. Clearly then, its capacity factor can never exceed 0.5 and its full load hours can never exceed 8760 by 0, which is around 4,300 hours. Okay, that is at the maximum possible. It was running at rated capacity throughout the daytime period. Even then, that's the maximum capacity factor it can deliver. Similarly, if you think of a hydel power plant, during the winter and the summer season, the river's flow is often quite small. So it cannot generate as much electricity it can generate during the rainy season where the river is in full flow. So clearly it delivers much lower than its maximum or rated capacity during the dry season compared to the wet season. Similarly, if you think of a wind power plant will not deliver any power at all, especially in calm days or calm hours, when there is not a lot of wind that is flowing into the blades of a wind turbine. So there again, its rated capacity will be much higher than the actual energy it is delivering in those hours. That is why the capacity factor Z and the full load hours are much lower than what you would expect if it was running full time at its peak power or rated power. So these things matter a lot. More than efficiency, we want to maximize Z and TF for a renewable power plant by suitable plant location. Because remember, renewable power is a distributed resource. So it is very location centric. In dry, arid regions, you will get much more solar energy than in high latitudes or in cloudy regions. Similarly, there are windy regions of the world and calmer regions of the world, and you will get better Z and TF values if you plant your wind turbines in the windier regions of the world. So these parameters become very important in renewable energy systems. So let's look into the current situation in terms of renewable energy contribution. So what is the share of modern renewable energy and how has that share changed in the last 10 years? So this is 2009 and this is 2019 and 2020 values. And you see that the modern renewables, okay, so what do we mean by modern renewables? Here it's given hydropower. Let me just see. Yes. So this is hydropower, renewable heating by biomass, geothermal and solar. So this is solar thermal. So we will see that solar energy can be used both as heat and in electricity generation. So this is the part where renewable heat is being used. And here is electricity generation by biomass, geothermal, ocean, solar and wind. And this is biofuels. So all modern biofuels, solar photovoltaics, electricity through wind turbines, biomass, geothermal, electricity generation through hydropower, and renewable heat generation through biofuels, geothermal or solar thermal systems together create the modern renewables basket. And in this modern renewables basket, we see that around 8.7% of the total energy generated in the world is from modern renewables in 2009. Okay, so some amount, but not a significant amount in that context, right? In contrast, 80.7% is fossil fuels. What is the rest? Primarily nuclear. Okay, so nuclear is neither renewable nor a fossil fuel, so we are separating it out. Okay. What is the situation in 2019? 11.7%, which increases to 2020 around 12.6%. So there has been an increase of around 3% to 4%. Not a significant over the last 10 years, but some increase has happened. And the renewable share has similarly decreased by around 1-2%, the fossil fuel share. Okay. But still, the increase has been modest and is far from what is necessary to effect the kind of zero carbon energy transition that we had been talking about in the previous few classes. This figure shows where the renewable transitions have happened the most and where there is still a long way to go. Okay. So the yellow countries are where more than 50% of the total energy comes from renewables. There are only a few yellow countries, particularly Norway, Sweden, Denmark. These are the countries which have a significant renewable share. Okay, around 50% or 40 to 50%. Brazil has also a significant renewable share with around 30 to 40% of its primary energy coming from renewables. Then comes China, India, Australia, these countries where the total renewable share is around 10 to 20%. And this is true for all of Europe as well and in US as well. Okay. Canada does slightly better with renewable share of 30 to 40%. But most of the regions of the world for which data exists, the renewable share is between 10 to 20%. There are countries that do worse. For example, Russia has a very low renewable share, so does the Middle East and the North African countries, as well as South Africa. So there are most of the larger countries and the more populous countries still do not have a significant renewable penetration. This is the growth in the share of renewables by sectors. Okay. So the power is blue. All right. Heating and cooling is red. Transportation is this bottle green color. Okay. And you can see that there are two parts in this curve. This is the total energy consumption that is happening throughout the world. Okay. Of this total energy consumption, 51% of the total energy is due to heating and cooling. Not only domestic heating and cooling, but also industrial heating needs. Okay, so as we discussed, many industrial sectors require a significant amount of industrial process heat to run their various processes. So that heating need is also part of this, along with domestic and commercial heating of buildings, etc. So that share is 51% of the total primary energy consumption in today's world, followed by the share in transportation, which is 32%. So energy consumed by cars, planes, ocean liners, etc. And finally is the electricity. How much? Around 17% of the total primary energy is converted and consumed as electricity. So even though electricity is very ubiquitous around us, as a share of the total energy, it's still significantly small. Okay. And in each sector, the penetration of renewables is different. If we think of the entire electricity generation as 100%, 28% of it comes from renewables today. So more than 1/4. And this number has grown dramatically over the last 20 years. So when we think of renewable electricity, wind electricity, solar, photovoltaic electricity, etc., this is where a growth in renewables have happened significantly. Contrast to that, the heating and cooling needs, renewables contribute around 11%, so around 1/10 of this sector, and in transportation it's even smaller, around 3.7%. So the reason why, even though renewable electricity share has grown significantly, the share of renewables in other sectors, which are much larger amount of the energy that is being consumed in the world today, have not grown as much. As a result, the growth in renewables is not as much as you would expect if you look at the electricity generation sector alone. Okay. And this shows this growth, that in 2015, the renewable electricity share was 25%. This has grown to around 28% today. Renewable heating and cooling share has remained static from 10% to around 11%. And the transportation share has grown from around 3% to around 5%, 4% today. Okay. So that growth needs to improve significantly in the future, and we hope that it does. Okay. So this was heating and cooling, transportation, and electricity. Here is more of a industrial wise distribution. So this is again the electricity sector, which has grown from 19% in 2009 to 26% in 2019. This is the building sector, where the growth has been from 10% to 14% of the total energy being consumed. This is industry and agriculture sector, where the growth has only been modest from 12% to 16%. This is the transport sector, growth has been from 2% to 3%. Okay, over a decade period. Okay. So again, a different story slightly here, but the same kind of overall picture. We need significant penetration is happening in the power sector, but lesser penetration in the other sectors. Okay, and that is something that we need to correct going on in the future. So again, a similar kind of a graph from 2011 to 2021. Here you see the renewable sector separated out into multiple segments. So what has grown actually that much? So in the renewable electricity generation sector, in 2011, 16% came from hydropower. That share has actually decreased to 15%. Okay. Solar has grown from 2% of the total electricity being producer to 10%. So a 5 times growth has happened in solar power plant generation abilities as a fraction of the total electricity generation between 2011 and 2021. Bioenergy has not grown significantly. Nuclear power has shrunk. Fossil fuel, of course, has shrunk to some extent. Okay. And overall, the share of electricity has grown from 20% to 28.3% in 2021. Okay. So the growth has largely been fueled by solar and wind electricity, which together now produce 10% of the total electricity being consumed worldwide today. These are the fastest growing sectors of renewable electricity globally. And this is kind of the annual addition of renewable power generation capacity worldwide between 2014 and 2020, distributed into solar, the yellow line, wind, the blue line, hydro, the green line, and biomass based power generation systems, CSP and everything else is the red line. And this is the annual capacity addition in gigawatts. And you can see the rapid growth in solar capacity addition till 2020. So in 2020, 256 gigawatts of total renewables was added, of which around 140 was solar, 90 was wind, and a small amount was hydro. Okay. Whereas here in 2014 they were more or less comparable. We can see over the last few years solar capacity additions have been the largest, followed by wind power capacity additions. However, the problem is even this growth in capacity additions is not sufficient. Okay. So if you want to achieve net zero by 2040 or 2050, you need to have tripling of the power addition rates in order to keep track with the net zero scenarios where the warming is below 1.5 degrees centigrade. So even the current rapid growth is not sufficient. We need to scale up this growth of renewable energy, power based renewable energy capacity additions from solar, wind, etc. in order to achieve our net zero targets and keep our warming to below 1.5 degrees C. And that is what IPCC is telling us. Okay. So while the growth has been good, it is not yet as good as we want it to be. Okay. So that's the problem.